if you look at the, this is a corollary. How would the thing become corollary? Yeah, this is, sometimes some people do it purposely. Some big theorem make a corollary. So the person becomes a person. Anyway, what I was going to say is that the statement of ratio test is parallel to the statement of the root test. Root test also says if lim sup of nth root of a less than 1, then the series is convergent. And if the lim inf of nth root of a greater than 1, then the series is divergent. Otherwise, nothing, no conclusion. So let's prove this thing anyway. Does he do it? Another consequence. Anyway, it doesn't. So let's do first one. So if lim sup a plus 1 divided by a, here it says the second. Then the series zero, 1, I don't know which one. Yes, it is going from M, no? Let's go from 1 then. This convergent, absolutely. For the root test, we proved that the nth root of absolute value of n less than 1, then the series n is convergent. Absolutely, so they are parallel. Proof, so suppose lim sup n tends to infinity a plus 1 divided by a is less than 1. Here actually we are taking non-zero numbers. In this case, in the root test you don't use non-zero numbers. Here, in order to divide, that's the only reason, nothing else. Let alpha is equal to lim sup mod a n plus 1 divided by a n. So thus alpha is strictly less than 1. Let epsilon is equal to 1 minus alpha divided by 2, then epsilon greater than 0. Now we are going to use that first part of the lim sup condition. Hence, there exists, say capital N, let's say belongs to is a plus such that mod of a n plus 1 divided by a n is strictly less than alpha plus epsilon, which is 1 minus alpha divided by 2. This is exactly 1 plus alpha divided by 2. What is that? 1 plus alpha divided by 2 is strictly less than 1. Observe that carrying is invisible. I have written no company for each simple and greater than or equal to capital N. Since there are such that like that. So the first we can say that a n plus 1 divided by an. This is less than 1 plus alpha divided by 2. Also, without writing so many things. An plus 2 divided by an plus 1. Again less than 1 plus alpha divided by 2. Again an plus 3 divided by an plus 2. Strictly less than 1 plus alpha divided by 2. A capital N plus N divided by A capital N plus N minus 1 strictly less than 1. This is not the best writing, but this language is easily understood. So you multiply. Here N plus 1, here N plus 1, cancel out N plus 2, N plus 2. By multiplying the inequalities, LITIES, we obtain what? A plus N divided by A capital N. Yes, should less than 1 plus alpha divided by 2 raised to the power N. Now let us substitute for the N plus N. Let's write M. So this is true for each N belongs to this N plus, right? Now if I substitute this way, I get N plus N is M divided by, no, I don't need divided by, I write it here, capital A-N, then 1 plus alpha divided by 2, simple N is M minus, then this is true for each M greater than or equal to M plus 1. Hence, mod AM is strictly less than mod AN divided by 1 plus alpha divided by 2 raised to the power capital N times 1 plus alpha divided by 2 raised to the power M for each M greater than or equal to M plus 1. This side we have absolute M. Since 1 plus alpha divided by 2 is strictly less than 1, geometric series converges. You multiply by this constant, it still converges. Since 1 plus alpha divided by 2 is strictly less than 1 and greater than 0, sigma n to 1 plus alpha divided by 2 raised to the power capital N times 1 plus alpha divided by 2 raised to the power N, and going simple and begins from I have here M, no, so let me M to be clear. This M going on converges. Simple and begins from N plus 1, not here. And these are minor details. Converges. Thus, by comparison test, that's by comparison test, this side converges. Mod AM m going from n plus 1 to infinity converges. I mean, mod A1 plus mod A2 plus mod A, capital N is a real number. Thus, n going 1 to infinity, An converges absolutely. Because I can always add some final counter terms, and it doesn't effect for the convergence. So this is the ratio test, first part. And shall I erase or you want to take a photo? So that you understand, right? Then the other part is, so I will erase it. If lim inf greater than 1, then the series diverges. So, as I told you earlier, for root test, we have the same similar statement. Proof. Suppose lim inf an plus 1 divided by an greater than 1. That alpha is equal to lim inf an plus 1 divided by an. Then alpha greater than 1. Thus, there is capital N belongs to Z plus such that an plus 1 divided by an greater than 1 minus, say, alpha 1 minus 1 divided by 2. Then there is envelope such that for each simple and greater than or equal to capital N, because alpha minus 1 divided by 2 greater than 0, that's my epsilon. So to simplify this thing, then we get, hence mod of an plus 1 is strictly greater than mod an times, when you simplify this thing, you get 1 minus alpha minus 1 divided by 2, how much? 1 plus alpha divided by 2. Something wrong? This is not alpha, this is alpha. Silly. Alpha plus 1 divided by 2. For each n greater than the root capital N. So this is true for any n greater than n root capital N. Thus, A, for instance, n plus 1 greater than mod A n times alpha plus 1 divided by 2. Similarly, mod of A n plus 2 greater than mod A n plus 1 times 1 plus alpha divided by 2. But mod A n plus 1 greater than that guy, therefore mod A n times alpha plus 1 divided by 2 whole thing square. Proceeding in this manner to make it short. Proceeding in this manner, it can be shown that, of course, you can write rigorous proof using induction, but at this point it is redundant. Proceeding, my spelling is correct. In this manner, it can be shown that mod of A n plus A capital N plus any simple n greater than mod of A n times alpha plus 1 divided by 2 question says the verb simple n. For each simple n belongs to say plus. Now if you want, you can conclude in two different ways. This series is divergent because alpha plus 1 divided by 2 greater than 1. If a smaller series diverges, bigger one diverges right away. One other way is showing is limit of a n, no room for limit to 0. Anyway, so I will say this implies, I will write that way, you can write it, anyway implies that sigma A n diverges. So proofs are not that difficult, and these two tests are very useful by the way when you are going to do complex analysis, real analysis, Lean soup, this result, ratio test, root test, everywhere they will be there. But in this case, not much recognition is given, no, I mean ratio test is a corollary effect. And in the remaining cases, we cannot assert any conclusion, he says. That is true because if you consider, say, example, consider the series sigma 1 over n inverse 1 to infinity. We know that sigma 1 over n diverges in how many ways? we can apply that. Yesterday you learned some theorem, Cauchy condensation test. By applying that, you can prove it. Another thing is this Cauchy. My Cauchy criterion, sigma n converges if and only if given in epsilon. There is an integer. After that integer, sum of any bunch of terms is less than 1. So, maybe now I need some lunch from I'm forgetting things. Anyway, the other one is you can show by the same method, you can show that this doesn't have bounded partial sums. We can prove that also. So both three methods are very important. Actually, the other two methods are far more important because that gives the idea of divergence. Sometimes when you apply theorems and say it works, of course it is correct, but to the contrary you may not know anything. Just like in a parliament in any country, those who can bullshit a lot have so much of power, so they just say nonsense. That's true in any country, including ours. So we know that this one is divergent. Also, lim sup n tends to infinity. 1 over n plus 1 divided by 1 over n is equal to 1. And lim inf 1 over n plus 1 divided by 1 over n also 1. Series diverges, both of them are equal to 1. So you can use either one. Similarly, sigma 1 over n squared converges. We know how to prove this one by how many methods? One is that applying Cauchy condensation test because this is decreasing, and you get when you apply this one, 1 over into the R converges if and only if R greater than 1. You can apply that in many ways. Converges similarly, it's not similar. We know that, let's write that tape over there, our video, and we know that sigma converges. Also, lim sup n tends to infinity. 1 over n plus 1 square divided by 1 over n square, and lim inf 1 over n plus 1 square divided by 1 over n square n tends to infinity. Both are equal to 1. So you have divergent series, so that lim sup lim min both are equal to 1. The convergent series, again lim sup min both are equal to 1. So if you go, if bullet 1 or bullet doesn't work, bullet 1 or bullet 2, what am I talking about? Maybe I'm thinking of a good line. So otherwise, this happens when you are trying to use lim sup ratio test as well as root test. Sometimes you get this is equal to 1. So no help to decide the convergence or divergence. then you have to play with other things. Anyway, so we have proved the ratio test and root test, and then proving that limit of n to the 1 over n is equal to 1 is actually a nice consequence of this thing. By the way, from that inequality, can you remember? Can I reach? I have to do this. I have to do this. You asked me about Riemann hypothesis or something, no? I will have to think about it during the weekend, see whether I can get to somewhere. But I wonder whether without knowing in complex analysis, we can get anywhere. This is lim inf n plus 1 divided by n tends to infinity less than or equal to lim inf nth root of n tends to infinity less than or equal to lim sup nth root of n tends to infinity. Let's put absolute because that's better. Lim sup n tends to infinity. We proved it, no? So something you can see from here is that if you have a sequence limit of n plus 1 over n is L, then lim sup of nth root of n is also equal to n. Right away. So there are some sequences I will give you. Actually, I was trying to prepare one today, but didn't have time or by the Ministry of Education called me and asked me whether I have written the complete writing. They don't have understanding that you cannot write mathematics looks like essays. So I'm busy, they are disturbing me. Let's see. Let me write a corollary here. See, you are with the corollary. If limit n tends to infinity, absolute n is equal to L, then what am I writing? N tends to infinity, n plus 1 divided by n. Say, oh, no, we don't need this. Is equal to L, then limit n tends to infinity, nth root of. So since I have to take absolute sign, then I write it is equal to L. There are many equations in maths. You want to find the limit of n root of n, but you cannot do so. That the way we did that, n plus 1 over n, and when the limit is L, then limit of n root of n is also equal to L. This is a very big application of these inequalities. I mean, here, though there are 3 inequalities, we prove only rightmost one and leftmost one because the middle one is obvious. and limit of nth root of 1 over n is equal to 1 is a kind of an amazing result, because when n tends to infinity, n goes to infinity, 1 over n goes to 0. So infinity to the 0 equals 1 somewhat. So these are called indeterminates. If I have had some time ago, I wrote some handwritten notes, if I can find it, I will give you a copy. All my other things I collected. And I like to prove that one before we get to the lesson. Differently. It's good for you. Another proof. Because you have to collect analysis. I have another proof of limit of n root of n root of n, it is equal to 1. Another one. I am going to write proof. For any n greater than 1, n to the 1 over n must be greater than 1. No? Or any n greater than 1. So let me say it is clear that that's how I write books. When you are writing the books, you do this a lot. You understand how any n greater than 1? It is clear that this. Or else you can put, it is clear that here also, either place you like. Anyway, thus, important thing is n to the 1 over n is equal to 1 plus Tn. Let's say, let me write let n greater than 1. Then thus, then for some Tn greater than 0. When n greater than 1 into the 1 over n cannot be less than 1, because if by any chance into the 1 over n less than 1, then you take n power, you get n less than 1. So it's not. Thus, n is equal to 1 plus Tn raised to the power n. So, if I want to prove that, by the way, limit of nth root of 1 over n is equal to 1, I have to show that limit of Tn is equal to 0. That's what I need to do. However, this is equal to 1 plus n plus n, am I right? I am silly. Ntn, no? I cannot remember binomial theorem, I guess. 1 plus ntn, now it is correct. N times n minus 1, 1, 2, tn squared, bingo, plus tn raised to the power n. Right? Therefore, all the terms in right hand side are positive. Thus, here it is, thus let's say hence n greater than n times n minus 1 divided by 2 tn squared. No? Now let since n greater than 1, I have written this is positive. Therefore, get 2 over n minus 1 is strictly greater than Tn square. Yes, you can cancel this n to this n, then 2 get n minus 1. This is true for any n greater than 1. Now you apply what? Some comparison test for limits. This one has a limit when n tends to infinity. This one also has a limit when n tends to infinity. Thus, limit n tends to infinity 2 over n minus 1 greater than or equal to
take the squeeze test.
Yeah, no, something the way
Tn squared is greater than
I
0.
Just write greater than 0. Otherwise, illogical. It will become illogical. Observe that limit n tends to infinity 2 over n minus 1 and limit 0 n tends to infinity both are equal to 0. Thus, hence by squeeze test x q u double e squeeze. Is there a e? Squeeze. Is it? No E. Is it? Correct. This one is here. Okay. Hence by squeeze test. Tn squared converges and limit n tends to infinity. Tn squared is equal to 0. Now we have to prove the limit of Tn is also 0. Let epsilon greater than 0 be arbitrary. Then there exists n belongs to Z plus such that for each n greater than silly person. For each n greater than capital N, Tn squared is strictly less than epsilon squared. And this is definitely greater than 0. Somewhere I said Tn greater than 0. Thus, for each simple n greater than capital N, 0 less than Tn less than epsilon, hence limit n tends to infinity, Tn is equal to 0. Thus, limit n tends to infinity 1 plus Tn is equal to 1 plus 0 is equal to 1. But 1 plus Tn is exactly into the 1 over n, that is limit n tends to infinity into the 1 over n is equal to 1. So this is a elementary proof of limit of n to the 1 over n is equal to 1. That one is an advanced proof, no? Applying ratio test. But it is a very important one to remember when you cannot find limit to see whether you can apply ratio test trick to get the limit. Very important. This is very important when you are playing with very difficult things to handle. This kind of ideas are very, very, very important. Okay, so now we have, there's another test by the way that this book doesn't have, because I was wondering whether you know all the tests. There are two tests that we cannot do right now. It's called Abel's test and Dirichlet's test. Product of A and B and type thing. It cannot be now. We cannot do it right now. But there is another test called limit. We have comparison test here. Limit comparison test. So let's write that and prove it. That's the only thing which came to my mind. Because I think I have my notes that I taught at Colombo University. But I am very lazy to look at these notes. Yeah, and they have very good problems also, but we cannot go for good problems in this book because you are getting 20 questions or 50 questions per week. Somehow, how can you do? This is clear enough. This is a very good proof.
You have to show that using induction, no? The
Binomial theorem.
second part is greater than n times n minus 1 or 2 p n square is less than that. Yeah. You have to show that using induction or something.
No, I'm sorry, I don't follow what you're saying. I'm sorry.
From the one before the last line
Yeah,
to the last line.
yeah.
To get that you have to use induction, no?
I mean, I am assuming that you know binomial theorem.
Yeah, I know the binomial expansion.
Yeah.
I mean the one after that.
Hence,
Yeah.
It goes without saying. I took this way, then I took the nth power of
Yeah.
either side. So when I take the nth power, this is binomial theorem. So n is equal to whole bunch of positive terms. Then n must be greater than any individual term. Right? Yeah, it is a good proof. Now we should go to limit comparison test. However, these books are very, not so sorry. The problems given in the book won't make you an expert in testing convergence or divergence of a series. So I have to give you problems every now and then. Make it work. Oh, all right. Shall I just? I suppose this book has a different goal, not analysis. I don't know what it is. Limit comparison test. Limit comparison test. Let E in this type, B in B2, C2, positive sequences. And let L be positive real number. You have two sequences, two positive sequences. Real number. Suppose limit n tends to infinity, a n by b n is equal to L. Then sigma a n, now series a, here sequence a, converges if and only if converges. If one converges, so is the other. Proof. L be a positive real number. Proof. There it is clearly, not clear, since limit n tends to infinity, a n over v n is equal to L. There exists, some say capital N belongs to Z plus, such that before writing the proof, can you see, when you have two sequences, positive, otherwise you cannot divide them. Then you can follow them are negative also, you can write that, but it follows from this. This is, if you have two positive sequences, then you divide one from the other and get the limit. Limit is, if you are getting a positive limit, then you know right away either both of them converge or both of them diverge. Then there are don't learn English from me because I say things right mindless there. Then there are equation belongs to Z plus such that a n by b n minus L is less than L by 2 for each n greater than n. Greater than, or greater than, or doesn't matter. Hence, a n by b n minus L less than L by 2, minus L by 2 for each simple n greater than. Thus, a n by b n is strictly less than 3L by 2, greater than L by 2 for each n greater than. So, E n greater than L by 2 times b n is strictly less than 3L by 2 times b n for each n greater than n. No? Now it is proved, no? If by any chance b n is convergent, from the right hand side one a n is convergent. If by any chance a n is convergent, right? This completes the proof. You already write that because you understand the rest, no? So this completes the proof. Again, there are so many, when you are testing, there are so many situations at which you apply this. So let us apply for very small ones that you can do otherwise, but to make sure that we do one or two examples after I do this. I think, except for the plus test and Nobel's test, you are done. Maybe now I will have to look at another book, not this book, to give you good exercises, or else I have to find my notes. Really easy, and we have in there, so much of dust and everything lying on the on some desk or on some table or somewhere. I have whole bunch of places where I kept notes and so on. This book doesn't give enough exercises for you to learn. I mean, he is interested in something else. That's why I always say, the goal of this book is not to make you good at analysis, but some sort of a very rigorous thing you are learning. This completes the book. So let's do one or two exercises. Yes.
Yeah.
Because of the new pens, you don't have to come to the board. No, I can erase.
Should have done that long time ago.
Yeah. We are too late to go for a new pen. I said one or two examples. So, discuss the DISCU, the convergence of sigma b. Just to show you, you don't have to do it actually. N plus 1 divided by n cube plus n square plus. For this you can do, but I just want to show you something. Because far away numerator looks like n, far away denominator looks like n cube. So far away this is like n over n cube. This is equal to 1 over n square. Therefore, if you say this is your an and this is your bn, limit of n over bn is 1. This one is convergent, therefore this one is, otherwise you can prove it, but I want to show you a tiny little application. Let n is equal to n plus 1 divided by n cube plus n square plus 1, and bn is equal to 1 over n square, for each n belongs to Z plus. Notice that an by bn is n plus 1 divided by n cube plus n squared plus 1 divided by bn is n squared over 1 is equal to n cube plus n squared divided by n cube plus n square plus 1 for each n belongs to n. Hence, limit n tends to infinity, an by bn is equal to 1, greater than 0. We know that sigma bn 1 to infinity sigma 1 over n squared That's why limit comparison test. You don't have to apply, but I just wanted to show you a very tiny example. That's why limit comparison test. Sigma n plus 1 2 divided by n cube plus n square plus 1. Anyways, this is a baby application of limit comparison test. This is how you do it. You look at the thing, if you can see it, that when it is so large, it is 1 over n square. This is one way of writing the proof. Of course, you can write n plus 1 over n cube plus n square plus 1 is strictly less than 1 over n square. That is also true. Then by comparison test, here in the way, since I took the limits, I wrote limit comparison test. Otherwise, you can say right away by comparison test and do it. For the other one also, let me write once. Let Cn is equal to 3n plus 2 divided by 7n square plus 1, and Bn is equal to 1 over n for each n belongs to Z plus. This far away, this is like numerator is like 3n, denominator is like 7n square, so it is like 3 over 7n. So you know that is divergent. Cn, Bn, then limit n tends to infinity. Cn by Bn is 3n plus 2. Ooh. Limit n tends to infinity. 3n plus 4 divided by 7n square plus 1 times n over 1 is limit n tends to infinity. 3n square plus 4n divided by 7n square plus 1 is 3 over 7 and not equal to 0. Good. Since sigma 1 over n diverges, we have that sigma 3n plus 4 divided by 3n square plus 1. And it is 2. There is equal. Again, this is a very application of limit comparison test. But in analysis, you don't come into cases deeper than this. And this is also you need to know. Because to become good at analysis, if you are very comfortable in solving little problems such as this, it gives you the strength. So it's very important. Of course, you know, you could have done, for instance, this problem here, n plus 1 divided by, what is this, n cube plus n square plus 1. You can say this is strictly less than 1 over n square. This is greater than 0. This is for any n. Then this one converges by comparison test. This one converges too. You would have said like that. Similarly here, 3n plus 4 divided by 7n squared plus 1. This is greater than Buffalo, New York. Okay, here is 3n. Here is, can I do it once, no? 7.
14n
n square plus again Simpson square. So then you get 3n over 14n square is 3 over 14n, and this is greater than 0 for any n. So this one is divergent, therefore this is divergent, here this is convergent, therefore these are very simple, but you need to know all of them. What else I was thinking? Here he doesn't give actual degrees, I guess. Let us be a real number. I did not give you the homework. I may forget, because I'm always thinking about that lunch. And I'm forgetting as a result. As a result, I'm forgetting. Let us see here. So he also emphasizes that integral test, we should do integral tests. Other things, did I do all of them? On the way, we did not prove real proposition 7.4.1. We didn't do it. And proposition 7.4.3, he says proof is optional. So we don't need to do it also. We have to do this. We did the correlation point A, we discussed that 7.3.7. Lemma 7.3.6, we discussed. Other things we discussed, no, all of them. Telescoping series on page 169, I don't know whether I discussed, but it is simple. So, on page 169. Go ahead.